board. Jeez. So I'll plot the coordinates first, or at least the vectors, based on the coordinates, and then we'll go from there. So we're finding the angle formed by each pair of vectors. Sometimes getting that visual is a good thing. You know, you could do it on Desmos or Geogebra. Easier to do on Geogebra, definitely, because of the 3D features. You know, if you needed to do it in a two-dimensional system, then Desmos would be the way to go. But if I'm plotting 3, -5, 1, what I would be doing is taking 3 steps in the direction of x, then 5 steps in the direction of -y, and then we create a parallelogram out of that. So I'm going to do it using the construction approach. Let me just actually draw a line segment. And let me turn that feature off, so I'll just take the whole graph with me. So I'd be looking at this, and then we have this guy here. Maybe a little on the long side, but we'll live with it. Kind of put us about right there. So that's 3, -5. Now 3, -5 in the XY plane. But I also want to go up 1 unit. So if I'm going up 1 unit, I'd want to get a sense of what that looks like on the Z-axis. Now, those little intersections on the Z-axis, those aren't necessarily vertical distances consistent with 1 unit. You can let the Z-axis be whatever you want in terms of distances, because that's just a perspective drawing. That's just the XY plane in the background of the Z-axis. So I can let 1 unit be whatever I want. All right. So just to be difficult, I'm going to let 1 unit be right here. All right, just kind of floating in space, and not really being difficult. It's more like just emphasizing that it need not be consistent with these points. You see these guys here? Those aren't necessarily tick marks related to the Z-axis. All right. The Z-axis is whatever I want it to be. So this would make this 2, 3, you know, based on the scale that I just established. That's what those distances would be. So this would be 2, 3, 4. You know, when I write it on that side, it looks like negatives. So let me just put it on the other side. All right. So what I'll do is grab a different color, say green for those keeping score at home. Draw a little line segment, poor quality line segment, undo. Better. That's that little green smidge of nothing that I just plotted. That's consistent with 1 vertical unit. So I just grab that over here and plot a point right at the tippy top. All right, so this point is 3, -5, 1. All right, that point just floating out there in space. To create the vector, what I do, I'll just do it in black. I connect it with the origin. And then just draw a nice little arrow at the end. Really emphasize that arrow. All right, and so this vector is 3, -5, 1. All right. Really want to get a decent handle on what these things look like in 3 dimensions beyond just, you know, what Desmos will show you, what Geogebra will show you. All right, because, you know, the reality is it's very easy to kind of lose sight of the internal workings of a function or a concept when you're just letting the technology do it all for you. So at least, you know, get a handle on it, and then let the technology do it for you. Now, we're looking for the angle in between that vector V. All right, so that's vector V. I'll just plot a little V right next to it, or just call it V, that is. Point V, vector V. And I. So I is just one unit along the x-axis. All right, so it's the vector 1, 0, 0. So that would put me right here. All right, and so what we're looking to do is determine the angle between those two vectors. All right, now they're askew. That's the thing, they're askew from one another. One of them is laying along the XY plane, and the other one is floating around in space. So not only, you know, if you're looking at, you know, my thumb and index finger as being on the XY plane, now you got to kind of look at it, you know, there's an angle between them. You can get a protractor on this and get the angle. But now I'm saying, all right, I'm going to push up my index finger out into space. So we have a different angle. The thumb is still facing in its normal direction, but the index finger is being pushed outward or upward. I mean, I'm not Gumby, so I can only do so much. What I can do is use my handy dandy manipulatives, my chapstick, you know, the XY plane. What it's saying really is, instead of being all on the XY plane, one of them is up in space. All right, still going to create an angle, still going to create a measurable angle. And in fact, from your perspective, it looks like, you know, I'm holding the greenish one, whatever color that is. I'm holding that at the same orientation. I'm only tweaking the Burke's Bees. So, but it's still creating an angle with the original, you know, the EOS one, you know, so we can still find an angle, long story short. So that's what we're going to do. The machinations or machinations, I never know how to pronounce that. Behind it is not too bad, but you do want to get a sense of what the underlying structure is. Otherwise, you know, like, you're not really going to get a feel for it. So what we're looking for is the cosine of theta is going to be equal to the dot product of V and I divided by the magnitude of V multiplied by the magnitude of I. Now, since a magnitude corresponds to a distance, that part shouldn't be too bad. The magnitude of I should just be 1. It's just 1 unit along the x-axis. You know, we can't call it the horizontal axis anymore, you know, because it's not necessarily horizontal. In fact, you could even think of the y-axis as horizontal if you're thinking of the whole xy plane as horizontal itself. All right, but I need to find the dot product between 3, 5, negative 1. 3, negative 5, positive 1. And 1, 0, 0. Okay, that's very easy. Because again, you multiply the corresponding parts and then add the results. Well, 2 of those corresponding parts are 0. Okay, so it's 3 plus 0 plus 0 gives a result of 3. All right, so the numerator is going to be equal to 3. For the denominator, I need the magnitude, again, of the vector V multiplied by the magnitude of vector I, which we know is going to be equal to 1. All right, so a little bit more work there, but nothing too crazy. All right, because, you know, you could even, you know, just find some space and chuck it in there. I'm going to do it overhead. Okay. So we're looking at 9 plus 25 plus 1. All right. A little dot product shortcut, but really it's just squaring each part, so it's not much of a shortcut. And so under the radical, we're going to get root 35. So we're looking at root 35 multiplied by the magnitude of a unit vector, again, is 1, because that's why it's called a unit vector. Okay, that's the whole reason. It is a vector that has a length of 1 unit. All right, so cosine of theta is going to be equal to that quantity. All right, so theta would be equal to the inverse cosine of 3 over the magnitude of 35, magnitude of the radical 35 is what I meant to say. And so now I need my Desmos. All right, so I don't need this right now. So just checking my mode, see what I'm in. I'm in radian mode. That's good. I could be in degree mode depending on how I want to represent it. Find the measure of the angles. I can go either way. I just want to be aware of what mode I'm in. Right? For the sake of coming up with a relatable answer, I'll put it in degree mode. Oh, that's just wonderful. I really love when that happens. There's something really wonderful about an app just full-blown crashing on you. Anyway, let me just double check. Degree, all right. So inverse cosine, 3 divided by the square root of 35. Pretty relatable angle. About 60 degrees. We could call it at 60 degrees. You know, 59.5, if we rounded it appropriately, it would give us about 60 degrees. Now, I'm not going to say my drawing was a work of art, but it's better than anything I would come up with by hand. You know, not like that. This is technically by hand, but I'm using an app to support my abysmal drawing ability. This is something. I mean, this is as close to computer aided as you can get without actually having the computer do the work for you, right? So, you know, this diagram is pretty spot on. And when you get that angle, hopefully you look at it and you say, yeah, I believe that's 60 degrees. That looks like it could be a 60-degree angle. All right. Now, I'm not telling you that you need to go ahead and draw a diagram every time it asks you to find an angle between two vectors, but sometimes for a little bit of peace of mind, it's a good way to go. All right. Now, number 9 is the angle between V and K. I'm sorry, V and J. Now, J is 0, 1, 0. So that's 1 unit along the y-axis. All right. So let me put my Desmos away for a minute. It just allows me to zoom in without restriction when I put it away. That's why I do that. All right. So here's what 1 unit along the y-axis would look like. That's vector J. All right. So when I'm looking for this angle, the angle between V and J, that's going to be a bigger angle. I'm going to use just a 1 arc to designate it, just because I'm using different colors, so there's hopefully no confusion there. But in terms of the computations, we're going to get something a little bit different. I mean, it's going to be the same level of difficulty. We've actually already done all the hard work. While I'm at it, though, I'm going to plot, let me get purple in here. I'm going to plot K, which would be that vertical one. Just tuck it in there. All right. So we also have an angle between K and V. All right, I just wanted to be done with the diagram drawing. All right. So when I'm looking at the angle, or trying to find the angle between V and J, for me, it's just a little copy paste action. Suppose it could be for you too. I'm going to take a whole chunk of it and then edit it as I go. All right, so it's not I, it's J, which is going to give me a different numerator. The magnitude of V is still going to be the same. So all of that stuff is going to stay put. All right. So that's going to give me the same stuff for K also. I just might have to organize it a little bit differently for spacing. All right, so we're looking at, like I said, we got J here. J was green actually. Oh, a little edit job here. This is going to be J also. And then K. But the magnitude of vectors I, J, and K, any of them, they're all going to be 1 because they're all 1 unit in length. All right, so that part is nice. We just got to figure out our numerators, which in turn is going to give us a different value for a cosine ratio, which in turn will give us different angles. So we're going to get a different one here and a different one here based off of what we come up with, like I said, for the numerator in each of these locations. You get the idea, though. I don't have to create boxes for every one of them. So, although it would look pretty cool. All right, so I'm bringing it back in. Well, as far as the dot product is concerned, if you just kind of play it out based off of what we did before, you know, you could even reproduce the computations, but in theory, you really shouldn't have to. Because if you take what we did earlier and replace the 0 with the 1, so basically swap the order, you're going to just pick up a -5 rather than a 3. Right? So you really shouldn't even have to do the work in order to come up with that -5. Right? The same idea would hold true for the multiplication involving a vector K, so the dot product involving a vector K. I'll show the work anyway, just so you have it, so my notes look nice, and you have it. But mostly because my notes, I want them to look nice. Right, but that's got to be something, if you really think about it, that you should be considering doing in your head. You know, coming up with that dot, because if you know that multiplying by I just really gives you, so dotting with an I mean something else, just gives you the X component of a vector. Dotting with a J gives you the Y component, and dotting with a K gives you the Z component. And then you got what you need. Oh man, this is just beautiful. All right, well, let's pause this video for a second.
Yes.
Oh, because it was when I crashed. Yeah. All right. So hopefully not too much time has passed. So yeah, I don't think they're updating the app very frequently. So I just tend to go towards the website when I deal with Geogebra, even on my mobile phone. I guess all my phones are mobile now. But what I'm going to do is I'm going to plot the original U and V. So I'll plot them as ordered pairs, and then I'll make vectors out of them. So 1, 6. And again, it defaults to calling it A and B, so that's fine. Next one, 3, -2. I have A and B, got my points. Zoom out, you see that they're floating around in space there. I'll get the vector. Requires a little bit of typing, but a little drop down. It's so troublesome. You know, we tend to want to stay away from it. All right. So what I do is I just kind of work my way around it. Sometimes it means living with, created a slider for every letter in the word vector. But I did that and I just deleted to go back and call it vector A. Although that doesn't seem to want to work. Let me just do it the way they want me to do it, I guess. And then it disappeared on me. There we go. Well, just hit the dot if it disappears. All right. So vector. I'll just do the point. You see, it does that. It's so weird. Better on a computer, obviously. A lot easier to navigate. But I kind of need to do this in order to get the point across. And then tap on this. Okay, so we got our vectors in there. All right. So the projection, without Desmos doing any of the computations for us, the projection is just the coordinate -9 over 37, comma -54 over 37. So I'll just type that in. It just doesn't like me. That's my my conclusion. Maybe I just got to get more of the word in there. -9, 37, comma, -54, 37. Need another set of parentheses. Literally killing me. Like literally. Nah. I gotta get the coordinate in first and then do it that way. I just gotta suck it up and deal with it. It's very frustrating, but it is what it is. All right, I'll just get the point in. Make sure I typed it in after all that. Be nice. Oh, it doesn't even want to take it as a coordinate. That's astonishing. It thinks it's a matrix. I mean, it's in vector form, which is great, but it's not. Oh, okay, I can work with it. I'm just going to turn these guys off. So, see that little teensy tiny vector that's just kind of hanging out there? That -9, 37s and -54, 37s. I guess I could turn the other one back on. So that vector A is going off in the direction of 1,6. It just sucks that it took like I wish Geogebra was a lot more user friendly, but then again, it probably would be a paid app if it was. So it's going off in the direction of 1, 6. The vector B is going off in the direction of 3, -2. Now, we got this little guy here, this vector, -9/37, -54/37. What that is a visual representation of the amount of vector that A is willing to spare to contribute to B's cause. All right, so B is inheriting really some of vector A. And what we wanted to do is determine how much of vector A. That's the component form. I'm sorry, not the component form, the magnitude of the projection, or the component of V upon U. But what this is a visual representation of what that vector looks like. All right, so basically it's giving us an idea that A is only contributing a teensy tiny smidge towards the efforts of B. All right, so if this is that case of 2 people pulling a boat, or people carrying a couch up a flight of stairs, or Tony Stark and Rhodey trying to pull up Mjolnir, this is basically saying, all right, one of them's doing the lion's share of the work, the other one is barely contributing anything. All right, so it sucks that the technology didn't really allow me to get that off in a crisp sort of way, but I got there eventually. It's just so clunky. Very frustrating. That's why I go with Desmos, because it's less clunky, but it's less powerful when it comes to the vectors in 3D. So it kind of is what it is, but we live with it, I guess. All right, so then we talked about the cross product. So I left you with number 2, which deals with the commutative property of the cross product, or is there a commutative property? Well, you just read down the page, it's kind of staring at you right there. It's like, is there a commutative property? I don't think so, because there's one right there that says anti-commutative property. So what we're going to do is kind of, quote unquote, discover that relationship. All right, so we'll figure out the cross product of U and V. All right, so U cross V. So IJK 0, 2, 1, 3, -1, 0. I'll get my absolutes going on here. So I want to find the cross product using the shortcut technique, because we don't want to have to waste our time using that nasty looking formula. This is really kind of bad enough. So I get my sets of vectors, well, 2 by 2 square matrices, but they are 2 column vectors. A little wonky, but we'll live with it. And just so I'm not here all night, or we're not here all night, I'm going to be here all night. Setting all this up, what I'll do is copy paste and just reorganize a little bit so we're ready to go for the UV. Oops, hello, that's not good. All right, so that's V cross U. All right, so I minus J plus K. Probably should have waited before copying and pasting. I'm gonna write that again. All right, so I get my stuff in. Oh, that stinks. Yep, froze. Oh, boy. Yep, it's crashing. So anyway, the the matrix associated with I is going to include every column except for the I. Right? So 2, 1, negative 1, 0. And I'll do both simultaneously. So negative 1, 0, 2, 1. For the J, every numerical column except for the J column. So 0, 1, 3, 0. This is one of those concepts where it's kind of, you know, just take my word for it for now. I'll explain it a little bit more down the line, but it's really more of a linear algebra concept. It's cofactor expansion for finding a determinant. So, but I do want to get into why the ij and k are allowed to be part of a matrix, which consists of column vectors when they themselves are vectors also. There's an interesting theory or thought process behind that. Right. So 3001 for k, 0, 2, 3, negative 1 versus 3, negative 1, 0, 2. All right. So I'm going to apply my diagonal down, diagonal up technique to come up with my coefficients. So diagonal down minus diagonal up. So 0 minus negative 1. So 0 plus 1, which is 1. So this is really just I. Minus diagonal down, 0, diagonal up, 3. 0 minus 3 is a negative 3. J, there's already a negative built into the model. So the two negatives will become a positive in a sec, but for now I'm just going to leave them. All right. Diagonal down, diagonal up, 0 minus 6. So negative 6. K. Result, I plus 3J minus 6K. Now, it doesn't take too long before you realize where this is all going, because the diagonal downs and diagonal ups are going to be reversed for the V cross U. So I'm going to have a negative 1 on the down tilt and a 0 on the upward. So negative 1 minus 0 is going to be negative 1. So negative I minus diagonal down is 3, diagonal up is 0. Again, diagonal down, diagonal up. 3 minus 0 is 3, so minus 3J. And I got the plus, diagonal down is 6, diagonal up is 0. So 6 minus 0 is 6, 6K. All right. So you can see that this is the exact opposite of the U cross V. All right. So this is the same as negative I plus 3J plus 6K, so negative parentheses, so scalar multiple. But since we know that I plus 3J plus 6K is the same as U cross V, we just discovered, you know, it's not a proof, it's just, it's like a kind of a, you know, the mathematical equivalent of a case study, you know. It's a justification, you know, a particular example showing how that relationship works. And that is that if you know U cross V, then you actually do know V cross U just by negating it. And that's where we get what's known as the anti-commutative property. All right, so it's not as simple as them being the same. There is a relationship though, and there is a known quantifiable relationship. And that's good news. It's always good news, right? Because something you can hang your hat on, right? Now, the problems below, so that's just one property of the cross product. The problems below have, references to all the other ones in some capacity. Some of them are a little bit easier than others, but if you look at, for example, number 3, use the cross product properties to calculate 2i cross 3j cross another j in R2. All right, it's great that it's in R2 because that at least tells us that I is 1, 0, j is 0, 1. You can work that out mathematically, or we could use some of these properties and see what's going on. All right. There are ways to visualize this, but with the advent of, well, it's not really advent, but using the prominence of technology or the more prominent use of technology nowadays, it kind of makes some things like I referenced the right-hand rule on I think the previous page, makes it a little bit antiquated. It's a nice fun fact, but it's not really 100% necessary because you can plot and get a sense of what's going on, especially in a remote environment. But I will talk you through that in a little bit. But what I wanted to do is show you how you can apply the properties here to get the solution in a reasonable way. All right. So we have 2i cross 3j. So let's focus on that because order of operations is still going to be a thing. There's no way around that. All right. And honestly, we don't want there to be any way around that. We want order of operations to be a thing because if they weren't, then math would break. And maybe that's what we want. I don't know. Everything you've been working this whole time to try to understand would be proved invalid. That's the definition of wasting your time. All right. So you look at these properties up above, and you see the 2i and the 3j. It's like, okay, everything seems to have u's and v's in it, except for the third one here, which has, in addition to the u's and v's, a c for a constant. So that seems to be a rule that we might want to apply here. All right. So it's just we're going to kind of do it in reverse. So I'm going to apply this rule, and I'm just going to take a piece of it. So cu cross v. That's the same as saying cu cross v. And I'll talk to you about streamlining that in a minute. All right. But basically what that's telling me is that I'm going to treat the I as the U. The 2 is really the C. And this whole shabiggity bangity boom here will be the V. Highlighters are great. It's almost impossible to screw it up now, because I'm going to replace every C, and watch me screw it up, by the way. I'm going to replace each of the C's with a 2, any of the U's with an I, and the V with a 3J. So this is going to become 2I plus cross, I almost screwed it up, 3J. All right, so I'm going to use that highlighter. All right. So another aspect of the rule tells us, and I'll just jot it down, I'll just do it beneath it. I'll just write it below. U cross CV is also the same as C times U cross V. All right? So now I'm looking at this new relationship, all right? And actually, you know what? I'm not going to get lazy. What I'm going to do is I'm going to rewrite this over on the side. And I'm going to take the 2. I'll leave the 2 out of bounds for now. I'm going to write it as I cross 3J. Let me just smidge this over a little bit. All right, because I want to be able to use my highlighter again. All right, so kind of looking at it sort of like a new problem. All right, so the 2 is irrelevant because I'm matching up I'm matching up the U with the I. All right, and I'm matching up the 3J, the 3 and the J with the C and the V. Ooh, that got really dark. All right, but I'm holding on to the 2 for now. All right, so this is going to clean up. So just this piece is going to clean up. The C is really a 3. The U is the I. And the V is the J. All right, but I still have that 2 there. Right, so I can't just ditch that. All right, so what I'll do is I'll take that 2 and just multiply it on at the end. And what I would get is a 6 times I cross J. And that leads us to the shortcut, I cross J, which tells me that I'm starting off. So I have this whole thing initially of 2I cross 3J. It's telling me that I can factor out, and I'm not really factoring it, but we're going to kind of use that word for lack of a better one. I'm going to pull out or factor out that 2, and I'm also going to pull out that 3, multiply them together, and that removes the coefficients. Now, I still have that cross J off at the end, but now I just made this a little bit simpler. Now, you wouldn't necessarily show all these steps. What you would do is say, all right, well, I got the 2 and the 3. That's going to make a 6. Let me just focus on the I and the J. That's really all you would do, or hopefully, anyway. I suppose you could resort to doing all this stuff, but that's not the point of all this. The point of this is to show you why or how that really works the way it does, all right? So then again, I still have that cross J at the end. And that's coming from right up here. All right, that's still part of the action. All right, so now what I got to do is I got to figure out what I cross J is. Right? Now, that's where that whole right-hand rule comes into play. Right? But you could also use Geogebra. Right? So let me just show you. I think I'll just start a new one. Don't save. All right. So yeah, it knows that. All right. All right. So. All right, so on Geogebra, and again, it's kind of a mess when we do it on here. We could plot 1, 0. Come up with a corresponding vector. And you see, I think it's just where I'm tapping it. Maybe that's the issue. Yeah, if I don't tap it on the word, it seems to be a little bit better. I don't know if that helps, but I got vector 1, 0, that's my I. And I do the 0, 1. And so vector, you go too fast, apparently there's a price to be paid too. Okay, yeah, so it seems to be that if you tap on the word when you're using this app, if you tap on the word, then it screws the whole thing up. But if you tap in like the highlighted space next to the word on the right, it seems to be a little bit better. All right, so the vectors are turned off, but I can easily just turn those back on. So that's fine. I got my two vectors there. Bring it in a little bit. So this is what vector 0, 1 and 1, 0 look like, right? So the question would be the cross product, since the cross product is defined as a vector that's orthogonal to two other vectors, then basically what we're looking at is a third vector that's either going to shoot off of the paper out towards me or into the paper away from me, right? So ij is either going to end up giving me k or it's going to give me negative k, right? Because that's the only way it could be perpendicular or orthogonal. So we're basically talking about the idea that if 1, 0 or I is along the x-axis, 0, 1 is along the y-axis, then the the cross product has to be along the z-axis, just a question of which way, in the positive direction or the negative direction. All right. So that's where the right-hand rule comes into play. Right. So the it's kind of tricky when it comes out. You know what I'll do? I'll get you a picture of it, because in the classroom I could just hold up my hand, but I tried doing that with chapstick and it didn't really do such a hot job. So let me pause the recording. All right, so here's the little diagram, a little right-hand rule action going on. I'll move it. Oh, hello. I'll be able to move the image. All right, so yeah, a little right-hand action. I got a diagram of a right hand, of the right-hand rule working out here. So maybe I'll just tuck it in this little space right there. All right, so what you would do is take, again, your index finger, place it along the x-axis. All right. Take your middle finger, put it along the y-axis. Now, you got to kind of go with it on this case. So you have right in front of me on my screen is where the XY plane is. So ordinary, y-axis, x-axis, just in reverse for you. All right. So I'm taking my middle finger and putting it on the y-axis. I'm taking my index finger and I'm putting it on the x-axis, and you could see that my thumb is pointing directly at me. Well, now maybe you can. I don't know. This is a lot easier to do in the classroom, but but that's the idea. So basically, this is getting across the fact that if we know that the cross product between I and j is going to be some form of vector k, it's just a question of whether it's going to be positive or negative, because it's coming out of the paper towards me, right? That's the positive direction, because we think of the XY plane as being flat horizontal. Anything that comes out of the paper is necessarily going up, right? If it were negative, it would be going down into the paper, right? So what we would get as a result here is a positive k. All right. And that's without having to actually compute the cross product. Now I'm going to hang on to that 6 for the time being. But what I want to do is tackle the k and the j, k cross j. All right. For that, I need 3 dimensions to work with. All right. Because what's happening is it's saying that we're in R2, but once I've computed the the cross product here, I've now incorporated R3, right? So it just made things a little bit spicier here, right? So K is vector 0, 0, 1. And J is 0, 1, 0. So if you want, you know, I think I'm a glutton for punishment here, but I'm going to go to Geogebra 3D. It feels backwards. All right, so I put in 0, 0, 1. 0, 1, 0. Create the vectors. Again, this is the fun part. Okay, my little theory about tapping the shaded area doesn't seem to be holding up. Nah. All right. Whatever. I'm calling it vector vec. I'm just gonna live with that. I'm not even gonna argue it. It's showing up. I'm gonna deal with it. All right. So vector, and then I slipped and tapped something incorrectly. So let me delete. Again, this craziness. It's just not letting me do it. All right. Okay, so let me delete this one. Little workaround. Delete, duplicate. Call it vector B. You get there eventually. The damn thing is what it is, you know. What can you do? All right, so I have these two vectors kind of living in space. I got that plane, the XY plane, but the one facing upward is K, and the one facing to the to the right is J. Right? It looks like an XY axis, but the X axis is actually coming out of the screen directly toward me. All right. So again, right hand rule, I'd place my index finger. You got to really contort it here. You got to really, these are sacrifices I make. You know, I'm going to really stretch it out. So placing my right index finger along the same line as vector J, my right middle finger, trying to make it not look like I'm flipping you all off, facing or running adjacent to vector K, and then now my thumb again is pointing directly out of the screen at me. All right. So it's going to be again orthogonal to the other two vectors, which has to put it along the x-axis or vector I. It's just a question of positive or negative because it's coming out of the screen towards me. It's going in the positive direction, which means that K cross J gives as a result vector I. All right. I still have that 6 there. So what I do is I just multiply it in the end. And now, without ever having to figure out a cross product, I'm able to come up with, well, the cross product. So without ever having to do it by hand is what I'm saying.
Professor?
Yes.
And if it was going inside the page, it would be negative? Negative Y?
Say it one more time.
If it was going inside the page, it would be a negative Y?
Exactly.
I?
Very good. You got it.
Thank you.
All right. So I wanted to not do any more of that because I'll come back to that next time with number 4. I want you to have an opportunity to try this one on your own before I, well, honestly, my fingers are starting to hurt. So I think I need like a good 5-day break before I can do another one of those problems. Kind of exaggerating, but not really. But we can talk about the magnitude of the cross product. Now, this is a really good concept because if you look at the rule here, you have the magnitude of U cross V is equal to the dot product of U and V multiplied by the sine of theta. All right. So this is strictly dependent on the level of difficulty of finding theta. If you could figure out the sine of theta, then you got what you need. You're in pretty good shape, right? Because anytime you can swap out a cross product for a dot product, you'll sign up for that any day, right? So that's really where the moral of the story is here. It's just sometimes it's more trouble than it's worth to figure out what the sine of theta is, right? But the one thing you want to have in your pocket, and I'll just jot it down here, is the rule by which we determine the cosine of theta. I'm sorry, theta. Cosine of theta is equal to U dot V divided by the two magnitudes multiplied. All right, which in turn means, you know, we've kind of worked with this kind of, you know, on the sly a little bit, but what it's telling us is that theta itself is really equal to the inverse cosine of all that stuff. All right, so we could actually figure out theta using this technique and then apply that, apply the sine function to it. All right, now things can get a little kooky here. You know what? I think maybe I'll save that for the same video that I make for, because that's on my list of things to do, thanks to the people who submitted that for typo bonus. The video that I'm going to make showing the derivation of the cross product rule, I'd also like to include this in that same video. So so we'll make it a typo, and it'll be just send me, make a video, please make a video for magnitude of cross product, and I'll know what that means. All right. Because I'll show you what happens when we actually substitute the inverse cosine in for sine, create a right triangle out of it, and do all the trigonometric manipulations. It's really actually a cool outcome. But in terms of coming up with answers, we don't really need to bother with that just now. I'll make it like fun fact territory, right? But if we're looking for the magnitude of the cross product, what we would want to do, thank you, appreciate it. So what we're looking for, and I can get rid of this now, at least for now. I'll bring it back as needed. So we're looking for the magnitude of cross product. One way to do it, you know, if you're in a jam, perfectly okay to find the cross product and then find its magnitude, right? But what you can do instead is figure out theta equals the inverse cosine of the dot product between U and V. So here's U and V. I'll just highlight it, make it pop a little bit. These numbers are really, really nice. All right, they're both along axes. All right, the right-hand rule, or, you know, regardless of whether you're using the right-hand rule, it doesn't make a difference, because if they're on an axis, if your angles are on, or your two vectors are on different axes, they're going to be separated by some kind of 90. Like whether it's a multiple of 90, like 180 or 270, whatever, but it's going to be some kind of multiple of 90, right? So here I'm looking at a dot product equal to 0 because if I multiply the corresponding parts and add them together, that's what I get. I get 0 over magnitudes that are not equal to 0, right? So 0 over not 0. Little shorthand notation. You can write it like that. I'm kind of mixing together probability and calculus, but the bottom line is it's already mixed together. The notation is pretty much the same. So this is saying 0 divided by something that's not 0. Hey, that works. That tells me that I'm dealing with something that's orthogonal, all right? So theta is going to be equal to inverse cosine of 0, which is going to be, if you want to go degrees, 90. If you want to go radians, pi over 2. All right, we'll say 90 degrees. It's orthogonal. But you could look at it and say, well, which way are we going? Well, we don't really care. We're just looking for the angle between the two. So we want the shortest angle between these two vectors. Now, if you're really concerned about it, what you could do is just draw a quick sketch. I'll just kind of rough it out over here. That's not what I wanted to do. That's what I wanted to do. That's not what I wanted to do. That's what I wanted to do. All right, so 0, 4, 0 would put you 1, 2, 3, 4 over here. And then 0, 0, negative 3, I'll just get a, a negative z-axis going on here. All right, so we have a vector going off in this direction, a vector going off in that direction. It's pretty clear that we're looking at a 90-degree angle in between the two of them. All right, but you could look at it and say, well, what if we went the other way? You know, what if I went this way? Yeah, that's great, but we're looking for the shortest angle between the two. All right, so we got our 90 degrees. Now what I'm looking for, again, is the magnitude, but that's based off of the product of the magnitudes of u and v in and of themselves. So magnitude of u, it's along the axis, is equal to 4. Magnitude of v along the axis is equal to 3. So if I want the magnitude of u cross v, we're talking 4 times 3 times sine of 90 degrees, right? Which is going to equal 12. Right? Now, I'm going to steal my own thunder a little bit here because I drew the diagram, so it's a good time to talk about it. And that actually saved me a little time later on. Because a big question is what is a cross product giving us? We know that is an orthogonal vector given two vectors, so that's fine. But the magnitude of the cross product is even more powerful, right? If I create a parallelogram, in order to find the resultant between these two vectors, if I create a parallelogram, I'm not going to actually display the resultant vector here, but I could, I suppose. If you look at this carefully, you realize, hopefully, that we have a length of 4, so a base of 4 and a height of 3. That gives an area of 12, right? So that parallelogram has the same area as the magnitude of the cross product between the two vectors that make up that parallelogram, right? Turns out that parallelogram is a rectangle, but still, it's still a parallelogram, right? So what we're actually getting here is a relationship that allows us to determine the area of a bounded figure based off of just simply finding the cross product's magnitude. All right, so it's pretty useful stuff. Right? Number 6 doesn't seem at first glance like it's related to number 5 because it says find a unit vector orthogonal to both A and B. It's like, wait a minute, a unit vector? That doesn't sound like magnitude of a cross product. If it's orthogonal to A and B, so the vector orthogonal to A and B would be A cross B. The unit vector is really just asking you, so I'll say unit vector of A cross B is going to be equal to the cross product of A and B divided by the magnitude of the cross product of A and B. All right, so this is a little bit of, I'll call it gray area, but I think it might be actually a little bit more black and white because you have a formula that'll help you come up with the magnitude. That's wonderful. But if you have to come up with the cross product anyway, then it's kind of like, well, why am I bothering? You know, that's part of the fun. You know, so making the determination of when it's appropriate to do one as opposed to the other. All right, so the cross product here, A cross B, again, IJK, 5, 2, -1, 0, -1, 4. So diagonal down minus diagonal up. I'll use my highlighter here judiciously. Oh, this is for I. So 8 minus 1, so 7, I. We got the minus built in for the J. So let me get, this will be the components for J. Diagonal down 20, diagonal up 0. So 20J plus, and then this is where it gets a little messy, but we can deal with it. For K, maybe I'll even just kind of box it in here. This is for K. Diagonal down -5, diagonal up 0. So -5 minus 0 is going to be -5. So let me make that a -5K. All right. So that's A cross B. Now, I think it would be kind of foolish to then turn around and say, okay, let me find the angle between A and B in order to find the magnitude of the vector A cross B to then plug it into the formula. So what we can do instead is just kind of off on the side here, compute A cross B's magnitude, which is the sum of the squared values under a radical. So we're talking 49, we're talking 400, and we're talking 25. Looks like what, 474? And so for my unit vector, let's kind of smidge things over here a little bit. My unit vector in the direction of A cross B is going to be each of those I, J, K coefficients divided by root 474, right? And this is the magic of the copy paste function. Except it's not feeling magical right now. I don't think I need this anymore. Smidge this over. Bring this in. Copy. Paste. 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 And I'll throw in some fraction bars for good measure. All right, because it's already in IJK form, so why not make use of that? You know, the i's and IJKs can be in the numerator, or you can rewrite it so that they're off on the side of the fraction. That part's up to you. And I don't have any particular feelings either way. So that would be the unit vector in the direction of the vector orthogonal to both A and B. Phew, Jackman. So that's some pretty strange stuff, but also pretty meaningful stuff, as you'll see, right? You know, it's kind of strange to think of this because we're, you know, I wouldn't say we're halfway through the course. We're getting there. We're getting closer and closer to the halfway point. But, and maybe we are, I'm not sure. But we're still in the kind of foundation building portion of the course. You know, because it's like, okay, cool, we learned about a unit vector. We've learned about cross products and dot products, and we plotted in 3D. That's all wonderful. You know, but what are we going to use this for? Because what we're going to have to do is talk about finding derivatives in 3 dimensions. And then when we do that, then all of this stuff kind of combines together in a beautiful way. And then you kind of see what this is all for. It's kind of like, I mean, the closest you've probably gotten to it before, I would say, is like Algebra 2, maybe not college algebra trig, but I'd say Algebra 2, if you took that in high school, where you did all the work with functions, quadratics, logs, and all that stuff, and then trig at the end, and then eventually you started doing stuff where you were solving trig equations, and those trig equations, you use things like, you know, the quadratic formula or completing the square, and you're like, oh, they go together. You could, like, it's like a crossover episode, you know. That was probably your first real experience with that. It's going to be more like that as we move forward. So, you know, a lot of this stuff's kind of bland, doesn't really have seemingly much application right now, but it's coming, and it's coming soon to a theater near you. Area of a parallelogram. I just kind of talked about that, but the derivation is a good one. Hopefully you'll like it, as in you'll understand it and look forward to seeing it on a test. The area of a parallelogram formula, as hopefully you remember, area is equal to base times height. All right, the parallelogram, just an ordinary parallelogram, and I'll just kind of chuck it off on the side here. Give you the classic parallelogram figure. Let me make it a little bit more classic looking. Kind of, sort of. Now that's probably the parallelogram you're used to, you know, the kind anyway. So what you would do is, and honestly, people kind of skip over this when they, you know, in geometry classes, they just kind of say, well, here's the formula for area of a parallelogram, and people are usually like, okay, sounds good. You know, that wasn't good for me. I didn't really like that. But what you were really doing is taking this portion of the parallelogram, picking it up and sliding it over to the other side. And that's how you know I didn't do such a hot job of drawing the parallelogram to begin with. All right. And so when I do that, ooh, undo. When I do that, what I'm doing is I'm getting rid of this part. So that's gone. My new parallelogram is made up of this stuff. Right? So when they say find the area of a parallelogram and it's base times height, as in, you know, the formula for area of a rectangle, you say, oh, well, that's because this length here corresponds to this length here, for quality squiggly bracket, which in turn is the new base of the rectangle. All right, and the height, even though it's outside of the parallelogram, it would still end up being the height of the corresponding rectangle that you would get if you took that little triangular piece, picked it up off the paper and moved it over, right? So basically we're saying, get rid of all this stuff. So this is not really there. And what you have really is a parallelogram, just looking slightly differently, all right? So that's why we're allowed to use A equals BH. Did you need to know that in order to understand the next couple of steps? Probably not, but it would be an incomplete derivation without it, right? So we're looking at a parallelogram here that is comprised of two adjacent vectors, V and U. All right, that U serves as the base. Right, so check. I mean, we'll have to make a minor adjustment to it, but we have our base. We have our base in symbolic form. Now, that vertical little line segment there, that corresponds. So if I were to take this, like I did before on the other side, if I take this triangular region here, pull it out, bring it over here, you would see that this line segment here is the same as this line segment there, both indicating the height. All right, so this is the height of the parallelogram, poor quality H. So I would just need an expression to represent that. Now, I already have it in the diagram, so I kind of stole my own thunder. But if I were to just kind of pull that triangle out, so what I'll do is I'll just kind of copy paste. Just pull it off on the side. I have V, I have theta, and I have H. All right. Now, V is a vector. If I want it to be a length of a side, it has to be a magnitude. But once I have that, I could use a little SOHCAHTOA action. Opposite, hypotenuse. All right, so the sine of theta, and I'll just jot it over here, sine of theta is equal to H over the magnitude of V, which in turn means that H is equal to the magnitude of V times the sine of theta. All right, now that base is really a magnitude of U. So I could chuck in little magnitude symbols there. Right, so now I have an expression that represents the base, and I have an expression that represents the height. So the area, base, magnitude of U, times height, magnitude of V, sine of theta. Which tells me that the area of this parallelogram has to be the magnitude of the cross product between U and V. All right, so that's a pretty sweet derivation. What it tells me is that if I'm dealing with a parallelogram, all I need are two adjacent vectors, find the magnitude of their cross product, and then we'll be in pretty good shape. That's all there is to it. Right. So 7 and 8 kind of work themselves out as long as you determine what side is, or what two sides are adjacent vectors, right? So a quick sketch goes a long way. You know what I'm going to do? I'm going to just grab that diagram that I did before. I just want to snag that, just so I have a little coordinate system to play off of here. I'm spending a lot of time copying and pasting this diagram. You know what? I'll take it as a typo. Let's get these babies in the notes themselves, you know. All right, so let me just pop in my little picture here. Takes up a little space, but it's not a bad thing. Scaling wise, you know, I might want to go by 2s here to get that R in there. That's fine. So that's what I'll do actually. So 1, 1, 0. So 1 in the direction of X. So we're going by 2s. So 1 in the direction of X, 1 in the direction of Y, creates a little tiny parallelogram here. And then 0 units up. So that means I'm living right on the XY plane. So that's point P. I'll label it up after the fact. 7, 1, 0. So every half box is worth 1 unit. So 1, 2, 3, 4, 5, 6, 7, 1, making a parallelogram, 0. Gonna put me right there. All right. I can draw a line segment between the two, so why not, you know? Uh, 9, 4, 2. So 8, 9. Oh, poor quality. 2, 3, 4. So that's going to get me right over here. And then I got to go up 2. So I have to come up with a predetermined distance for 2. I'll call this 1, 2. So whatever that distance is, and that's where a little construction action goes a long way. So I'll draw a vertical. Oh, what on earth? Oh, I know what happened. Okay, so I'm going to have a little point here. It gets a little blurry, a little tougher to see, but it's there. Just got to believe it's there. And then the last one is 3, 4, 2. Right, so 9, 4, 2, 3, 4, 2. So I'm doing the same thing. I'm just not going out as far. All right, 3, 1, 2, 3, 4, puts me about right here. And then again, I'm going up 2 from there. All right. So what I'll do is I'll connect these with green line segments. So here, here, and here. All right. Now let me bring it in so there's a fighting chance of actually seeing what's going on here. So it's kind of tough to see, but we have a parallelogram that's got 2 sides. Let me get the black pen going here. So 2 sides here, these 2 guys. I'll highlight it in purple here, a little thinner. That's my parallelogram. So it's kind of like a little sheet of paper, little sliver of paper, but it's kind of held at a slight angle, right? Like a ramp. You know, one of them's on the floor, one edge is on the floor, the other edge is elevated a little bit, right? That's what's happening there, right? So like a little tricky visualization kind of thing going on there, but I think a necessary one to get an idea of what's really happening, right? So I got to find the area of this thing. The whole point behind it is getting a sense of what am I finding the cross product between, right? So that's where I go back into the diagram The first point, I believe, was P. Now let me make that a little. So that's point P. I think it was Q. Q was 7, then R was 9. The 9 went, okay, so P, Q. This was R. And this one over here was S. Right? So what I would want to do is find the vector going from P to Q. Then I want to find the vector going from P to S. Because those would be corresponding, or not corresponding, adjacent vectors. They'd be pinned at the same location. And then once I find those, I'd find the magnitude of the cross product between them, using whatever technique makes sense. Right? So P to Q, 7 minus 1, 6, 1 minus 1, 0, 0 minus 0, 0. And then P to S, 3 minus 1, 2, 4 minus 1, 3, 2 minus 0, 2. All right? So like I said, I got to find the cross between these two things. Or well, at least the magnitude of the cross between them. This is my ultimate objective. All right, so I could find the dot product between the two of them and multiply it by the angle in between. You know, it's just one of those things. It's like, well, what's going to be easier? You know, we don't really know until we dive in. So, you know, it's paralysis by analysis. So pick a method and just dive in. I'm going to use the angular approach, right? So cosine of theta, well, theta, really. I'm going to go right for the shortcut. Inverse cosine. The dot of P and Q. 6 times, so we're going to multiply down the lines here. 6 times 2 is 12. Everything else zeroes out, right? Then on the bottom, I need the magnitude of each one. It's the product of the magnitudes, right? Well, one of them has a magnitude of 6. The other is going to be 4 plus 9 plus 4, so root 17. All right. The idea there is like, okay, let's see if we can save ourselves a little time and energy, you know? So inverse cosine, oops, there we are, 12 divided by 6 radical 17. And we're talking about 60 and change. All right, that's good to know. If I want to find the magnitude of the cross, let me get rid of these this interrogative. What I'd be looking for is the magnitude of Q, sorry, times the magnitude of PS multiplied by the sine of theta. All right, and with this guy up here, let me box it in red for those keeping score at home. This is my theta. All right, so we got a little nifty workaround that's coming up right there, because I know that the magnitude of PQ, I've already figured that out, is 6. Magnitude of PS, rad 17, and we're going to multiply it by the sine of theta. So what I'll do is I'll go back into my Desmos, and instead of trying to duplicate and copy and all this stuff, I'll just add on to this computation. So I'll take in the 6, a radical 17, not literally add on, I'll like incorporate, right? Then I'm going to multiply by the sine of this bad boy right here. All right, so all I did was I chucked on all the other trimmings, you know, all the little bells and whistles. And what we come up with is the magnitude of the cross product. Sorry, I put cross product here, but it's really the magnitude of the cross product. Let's notice that is about 21.6. All right, they don't have any units, but this is representing an area, so square units. All right, so could you have done it a different way? Yeah, I mean, that's kind of the theme of the course. You could do it another way, right? Yeah, you can always do it another way. As long as it's a way that doesn't involve you trying to skimp out on doing the quote unquote calculus, although this doesn't involve calculus yet. You know, so my only requirements when it comes to approaches that you take is, you know, like that question involving, you know, forces, tension, and things like that. I just don't want you using a physics formula to do it. I want you to do it the way that we talked about it in class, because that's going to support our calculus learning. Right. Now the next one there, I'm going to put a star on. It's actually pretty straightforward, but it doesn't seem like it would be, because you're like, wait, we just talked about parallelograms for a ton of time, but we didn't talk about triangles. What's up with this? Just remember, a triangle is half of a parallelogram. So what you could do, and I could even kind of get you going, at least with the first step here. You take this triangle, you can kind of reorganize it a little bit. And what you get, it's a poor quality parallelogram. I mean, I'm trying my best. So that's what the parallelogram roughly would look like, right? So using what we just talked about related to parallelograms, we have two adjacent sides here, for example, this guy and this guy, the vectors corresponding with those adjacent sides. This would be PR, and this would be PQ. Find the magnitude of the cross product between P and R, PR and PQ. That's going to give you the whole shabiggity bang. It's going to give you the whole parallelogram. Instead, you only want half of it, so you just pop in a 1/2 in front. So you still got to do the work, but at least there's a little end game there for you. So that's where we're going to leave it for tonight. Next class, we'll pick up with the triple scalar product, and then we'll get into vector valued functions, which is pretty interesting stuff. And then we'll go from there. Right, so I'm going to stop the recording.